So what we're going to talk about today is the Waroona case study. So it's a case study that we did on the Waroona fire, which was south of Perth in January 2016. And the reason we were looking at it as part of the Coupled Fire Atmosphere project was because during the event there were 4 episodes of extreme fire behaviour, and the people who were managing the fire really didn't understand why the fire did the runs at the time it did, when it did, and why the fire behaviour was extreme at certain times. And when they did the reconstruction, there were periods of fire spread that just didn't reconcile with the surface observations. So we've done this as a case study as the first stage of the project. We're now getting some simulations going with access fire, and we've actually got a fire now running in the coupled fire model. It's going to take quite a lot more work to get useful results out of that, but we're hoping that by the end of next year we'll have some really good simulations to show. So I think one of the important things to recognise in this case study was that we did it as a collaborative work. So there was myself and Jeff and Robert in the Bureau in the research side, Brad Santos, who some of you might know, who's in Western Australia in the severe weather section. So he provided a lot of the local weather knowledge, and Lockie and Neil from what was then DPAWS, which has been rebadged, and their input was all the fire behaviour. So I think the main thing is that we couldn't have done it individually without being able to consider what was happening with the weather and the fire behaviour at the same time. So the collaboration in this was really important. So if we look at the first slide, it should be a map up of the Perth and Dwelling Up and Wager Up area. So one thing was this, you can see the fire ignition in there. The fire did burn nearly 69,000 hectares in total, and most of that was in the first 2 days. So the actual event ran for about a week, but it was really the first 2 days of the fire that we were really interested in terms of the reconstruction, the behaviour that happened. And most of that was when the fire was running on the plateau, and then when it got down onto the plain, it was a lot more sort of typical fire behaviour, and there wasn't as much unexpected activity. You can see the serpentine radar on the map. This was one of the first fires where we've seen inside radar coverage. Obviously the Pinery fire last year just north of Adelaide, that was inside radar coverage as well. Some of you might know that Nick McCarthy is doing work up in Queensland, driving around looking at fires with a radar mounted on the back of a truck. So we're learning more and more about particularly plume behaviour from some of the radar data that we're getting, and there's some really interesting radar stuff that we can see out of sort of to reconcile with the fire behaviour. So on that map you can see position of the radar, the nearest automatic weather station that the Bureau owns at Dwelling Up, and the one at Wager Up, which is owned by Alcoa, the mining company, and then the 2 towns, Waroona and Yarloop. So if we flick to the next slide, this is basically a different presentation of the reconstruction of the fire spread that was done by DPAWS, and it was Lockie and Neil and Brett and a couple of other people who worked on that. So you can see the coloured contours. The red outlines are the first day of the fire, the orange is the second day of the fire, and then after that we didn't really consider that time in the case study. So the fire actually ignited on the evening, the Tuesday evening, and it wasn't seen or wasn't sort of identified until about 6:30 on the Wednesday morning, and that was when it did its first run during the day. So if we go to the next slide, please. So the first period of extreme fire behaviour was the Pyro-CB on the Wednesday afternoon, so Pyro-CB, Pyro-cumulonimbus. What we can partly see from this slide, which we can also start to see in the other imagery that was taken, is that this storm was actually multicellular. You can see a couple of different outlines in the cirrus cloud. And so the multicellular nature tells you that there were separate pulses in the energy that overcame the inhibition there. So it wasn't just a single pulse and then the fire ran. So that satellite image was taken at 18:10 local time, so well into the evening. Western Australia doesn't have daylight savings. But at that time, the fire danger, the FDIs were actually dropping. And that was one of the big things with this case study, was that there really wasn't any correlation between what the FDIs were doing and what the fire behaviour was. So if we go to the next slide has got the F-160 from Perth, so not very far to the north. And you can see from a meteorological perspective, it's a pretty unstable atmosphere. So there's a fair bit of cape in there, but there's also not a lot of low-level moisture. So there was a fair bit of normal thunderstorms on that day, but most of them were about 350 kilometres or more to the north of the fire. There was nothing else around the fire area. So in that vicinity, there was really nothing to trigger a thunderstorm apart from the energy released by the fire. If you look at the low-level moisture on that trace, there's really no indication from that you had enough moisture to produce a fire. So the fire must have been releasing a lot of heat in order to overcome the inhibition. For those who are familiar with looking at F-160s, on the right-hand side there, you've got the wind profile, and what we can see in that is the winds actually change direction quite a lot with height, so we call that the shear, quite a lot of shear in there. And what that means is that the plume can actually be quite organised. So any kind of wind shear is always going to help your organisation of a plume, and we see that in normal thunderstorms. And we'll show the video a little bit later that was taken of the fire, and you can really see that there's a lot of rotation in there, and the vertical wind profile is part of the mechanism for that. So if we flick to the next slide, one of the questions we asked was what triggered the Pyro-CB? Why did it pop when it did, when there was obviously no strong forcing mechanism? And these simulations, have you got a picture of a high resolution access simulation up now?
Yep.
Yep, great. So what we're looking at here is a cross-section across the scarp, west to east, from left to right. So hopefully you can see the edge of the scarp there. And this is through the area that the fire was. And what we're looking at here is potential temperature, which is just temperature adjusted for height and pressure in the atmosphere. And what you can see, hopefully, there's a green area that's coming in, and that's the sea breeze front. So the cooler air, the greener air is cooler air coming in the sea breeze front. And where that up motion is, that's the leading edge, the circulation on the leading edge of the sea breeze front. So those contours really sort of are the nudge, if you like, or the push that set the Pyro-CB going. And we look at the timing of that, then it matches the timing of when the Pyro-CB triggered. And we've seen this in other fires as well. The Sir Ivan fire, when that transitioned to Pyro-CB, that was also on the leading edge of a front. That was the synoptic front rather than a sea breeze front. And there's a couple of other cases as well. So there's certainly a growing body of evidence of different studies where when you've got some kind of a frontal change coming in, whether it's a sea breeze front or a synoptic front, that can be part of the trigger for Pyro-CB, or certainly stronger vertical convection than what you have in a fire until that time. So if we go to the next slide, these are the observations from Wagerup Automatic Weather Station. Hopefully you've got a plot from an automatic weather station up on the screen now. And this was from midnight on the 6th of January to midnight on the 7th of January. And what we can see in here is in the afternoon, at around about 4 o'clock in the afternoon, if you look at the temperature, which is the top plot, there's a little drop in temperature. And that's when the sea breeze front came in, and there's also an increase in relative humidity, which is partly from the temperature and partly from the increased moisture on the sea breeze front. When you look at the winds through that period, we had an easterly wind, and that flicks around to a southwesterly wind when the sea breeze front goes through. And the timing of that pretty much matches what we saw in the simulations in terms of the timing of the sea breeze front moving across the fire ground, and it also matches the timing of the Pyro-CB developing. Interestingly, if you look at the wind speed and the wind gusts, which is the bottom plot, there wasn't a lot of wind. There's less than 5 metres per second of wind. So there's not a lot of wind, and there wasn't a lot of wind near the surface in the whole environment to drive fire spread. So this was really a plume-driven fire rather than a wind-driven fire. The wind certainly wasn't, the surface wind certainly wasn't a factor. If you think back to what we were looking at with the F-160, there was a bit of wind above the surface. So if anything, the plume was actually entraining the wind from above the surface, so the 2,000 foot or 3,000 foot wind, and that was mixing down into the back of the head fire, and that was helping drive it. But certainly the surface winds were not a significant factor. So if we move on to the next slide, which is a radar image. And this is a radar vertical cross-section, so on sort of the lower plane we've got the near-surface radar scan, and then this taken a slice through in the vertical. So we're looking at the vertical structure of the Pyro-CB. Now there's a red circle to the bottom right of the screen, and that red circle is actually showing where the surface fire is. So that's our surface fire position, and then we've got the town of Waroona. So noting here that there's actually quite a big separation between where the surface fire is and when the downdraft from the Pyro-CB is coming down. So it's certainly not a case of it goes up and down straight over the fire. There's that separation because the actual plume or the Pyro-CB and the moisture in it is actually transported downwind by the winds above the surface. So you can get outflows which happen a considerable distance away from the fire front. So if we go to the next slide, which actually shows that when the Pyro-CB outflow hits the ground, so we've got another cross-section, but that outflow, the red bit is the outflow from the Pyro-CB hitting the ground, and you can see that that's a distance of several kilometres away from where the head fire is. So the actual fire is where the red circle is, and the Pyro-CB outflow is coming down several kilometres away from that. And that's at nearly 7 o'clock in the evening, so quite late in the evening when your FFDIs are going down. So flicking across to the next slide, it should be a picture of the Pyro-CB cloud. This was a still taken from the video that Darren McCarr at Farmhouse Films showed, and this was around sunset. So you can see, hopefully, in the Pyro-CB shield, there's a couple of separate shields in there, which indicates the multicellular nature of the storm, and also a lot of rotation and a lot of organisation to it. Now, down the bottom of that slide, I've got the observations from dwelling up AWS. So the FFDIs at 6 o'clock in the evening was 19, and at 7 o'clock in the evening the FFDIs were 15. So no correlation there between the fire behaviour and the development of a Pyro-CB and what the surface FFDIs were indicating in terms of your fire activity. Now, interestingly, the maximum in the FFDI was 40, and that was a couple of hours earlier at 4:15 in the afternoon. And at that time, the fire wasn't moving as fast, and it certainly wasn't releasing as much energy as what it was in that evening period. All right, any questions?
None so far.
No? Okay, so if we flip...
Oh, hang on, we have one.
Yeah.
Mika, Jenny here. Just
Hi, Jenny.
to clarify, you're saying the max FFDI was at 4:15. That was when the sea breeze came in? Is that...
Yeah, it was actually just ahead of the sea breeze. Yep.
Yeah, okay. Thanks.
Any other questions?
Yeah, Mika.
Yep.
I'm Mika at Queensland. I've just got a question. I guess one part of it showed with the depth of the sea breeze played a pretty critical part in this. I guess if it was shallower, it may not have necessarily kicked off this thunderstorm, but it seemed like the height of the sea breeze played a pretty critical part in kicking it off. Would that be correct?
Good question, but it wasn't, I guess, we've seen frontal changes which are quite weak setting off Pyro-CBs, and also frontal changes that are quite strong setting off Pyro-CBs as well. So the winds behind and ahead of the sea breeze, I think, were around about the 10-15 kilometres an hour mark or less, whereas we've seen synoptic situations where you can have much stronger winds, so up around 30-40 kilometres an hour ahead of, and then just pulling numbers out of my head here, I'd have to go back and check the numbers. Where you've also seen Pyro-CB. So it seems like, depending on the circumstances, you can get a front triggering, no matter whether it's a weak change or a strong change. But it might just be that little bit of convergence that gives it an extra nudge, particularly if you've got an unstable atmosphere over the top already.
Yeah. So the second question, I'm not a Perth guru, but is dwelling up down on the coastal plain and not up on top of the ridge?
Sorry, you're breaking up a bit. Can you say that? Is
dwelling up down on the coastal plain, or?
No, if you flick back to the second slide, I think it was, which had the map, you can see that Dwelling Up's up on the ridge, and the Wager Up automatic weather station is right at the bottom of the slope.
Yeah, I think I got the tour. Oh, that's all good.
Yeah. So Dwelling Up's up on the scarp, and Wager Up is literally right down the bottom of the lee slope of the scarp.
Thank you.
Mika, Andrew here from QFES.
Hi, Andrew.
Thanks for making sure we got on. Just checking, did you say that there wasn't a relationship between the fire behaviour and the Pyro-CB, or were you saying between the FFDI and the Pyro-CB?
Between the FFDI and the Pyro-CB, yeah.
Yeah, sure.
So when they did the reconstruction, I think at that point the fire was either running at 2,000 or 3,000 metres per hour. So when they did the reconstruction and they looked at the surface winds, you couldn't reconcile the speed of the surface winds and the speed of the fire spread through that period. But if you go back to the slide which had the trace on it, you can see that above the surface, so around about 600, 700 hectopascals, so around about 3 to 5 kilometres above the surface, probably even 2 to 5 kilometres above the surface, there's 25 odd knots of wind in there. So we'll talk about that a little bit more when we look at the event the following morning. But you know, that's when you get your forecast, that's the winds above the surface that we've often got in there on your spot forecast, and also hopefully on the daily ratings. You've got the winds above the surface. And what we've seen from other cases, and this matches what we see in thunderstorms, is that the fire plume can actually, the vertical circulation, the fire plume can actually mix those winds that are above the surface down into the back of the head fire. So it's not your surface winds that are driving the fire, it's the winds that are above the surface. Does that make sense?
Yeah, so the FFDI is not going to pick that up.
No way, because your FFDI is only looking at the surface conditions. So when the forecasters are doing a forecast, typically on a day where we've got a strong jet, they'll mix those winds down to the surface when they're doing the forecast grids, the GFE grids, or the Australian Digital Forecast Database grids. But on a day like this where you don't have a really strong mixing mechanism, particularly in the afternoon, it's not generally, there's not really a meteorological mechanism to mix those winds down to the surface. Whereas once you've got the fire there, the fire provides the mechanism to mix the winds down to the surface if you've got a decent plume which is going up to, you know, above the top of your boundary layer, so 4 or 5 kilometres or higher.
Yep, so there was good correlation between the plume and the fire severity, just not the FFDI.
Yep.
Yep, okay, thank you.
That's all right. Any other questions? No. Okay, so if we go back to the slide which has got the Ember storm, the first Ember storm over Waroona on the Wednesday evening. So in the fire reconstruction in the reports, there was an ember shower that was reported after about 9 o'clock in the evening over Waroona. Now, when we look at the timing of this was after the Pyro-CB decayed. So the Pyro-CB, when you look at the radar, it had actually decayed pretty significantly by 9 o'clock in the evening. So you couldn't say that the ember shower was outflow from the Pyro-CB because there was a time lag in there. And if you consider your burnout time for your embers to be the order of a few minutes, then it wasn't possible for the outflow from the Pyro-CB to produce an ember storm after 9 o'clock in the evening. Now, at this time, the incident management team had information that the fire was actually 13 kilometres further east. So when they got the reports of the ember shower, they didn't understand how it was as close to Waroona as it was. Now, when you look again at the report that was put together, there were a couple of observations of lightning ignitions that were downwind of the main head fire. So they would have been closer or in between where the fire was and where the town of Waroona was, and they were possibly along one of the little gullies in there. So what it looks like happened is the Pyro-CB lightning strikes and the Pyro-CB actually ignited a new fire closer to the town of Waroona, and then you had downslope winds mechanism driving the embers closer to the town. So if you flick to the next slide, which is another radar image. You can see the town of Waroona is circled in red, and just to the south-southeast of that, there's in the velocity scan, which is the blue and yellow one, there's a convergence area. So in there, what you've got is convergence, and where you've got convergence, you've got a lifting mechanism to lift embers up. So the surface fire, which was just upstream, or probably the new ignitions from the lightning strikes, which is upstream, and you had convergence in that area, which produces a mechanism for ember transport. So flicking across to the next slide, which has got lots of green on it, these are simulations that Robert did using the access model at high resolution. So I think these ones were 400 metre resolution. And again, we're looking at a cross-section across the scarp, and it's a vertical cross-section of wind. Now, hopefully what you can see in there is that just above the top of the scarp, or just above the lee of the scarp, or above where the town of Waroona would be, you've actually got a maximum in the winds in there. And that's the downslope wind mechanism. So when we talk about downslope winds, here in Adelaide we get them, we call them the local gully winds. In Perth they're called the scarp winds. And effectively what happens is when you've got any kind of easterly flow which is across the top of the ridge, you've normally got cooler air to the east and warmer air on the coastal plain. And in the evening, what we tend to get is a temperature inversion developing near the top of the ridge. In Adelaide it tends to happen when we've got a ridge of high pressure, so you've actually got a subsidence inversion. In Perth it looked like a combination of a subsidence inversion and a radiation inversion. But what you end up with is an inversion or a temperature differential that's sitting just above the top of the ridge, which acts as a lid. So the airstream, when it's coming up the back of the hill, is squeezed in between the top of the hill and the temperature inversion. So it's just a gap of a few hundred feet that's sitting at the top of the hill. And as the air squeezes through there, it then hits the lee slope and it accelerates downward in a really gusty, turbulent flow. So what we can see from the simulations was that even though there wasn't a lot of wind in the surface wind, you had a lot of wind sitting just above the surface, and that's in the vicinity of the fire plume. So if we go to the next slide, which is another cross-section, what we can see in this one is there's a little white ellipse in there, and that's showing you a hydraulic jump. So the hydraulic jump is essentially the flow response to being squeezed through that narrow gap between the top of the ridge and the temperature inversion. And in some ways, it's not very scientific, but think of it as a bounce or a wave form that happens in response to the flow adjusting to going for a squeeze through a really narrow gap to having a much wider area. And there's been quite a lot of work that's been done on these hydraulic jumps, mostly for aviation purposes, because both in Perth and in Adelaide, when you get a plane that's flying through those hydraulic jump areas, it produces severe turbulence, and they can fly through that region when they're on approach to the airport. So they've done transects where they've flown backwards and forwards and measured what the vertical velocity is above those scarp regions. Now obviously if you've got a lot of vertical velocity that's sitting just above the surface and you've got a fire plume there, then you've got a mechanism for lifting up embers and depositing embers down within close proximity. Now, some of you might have seen the plume work that Will Thurston was doing using a large eddy simulation model. He did some really pretty animations of plume work and putting traces in an idealised plume. But when you think about a fire plume, what happens is you've got your embers that are being lifted up and they're being transported vertically, so they can get lifted up maybe even a couple of kilometres into the air. They get circulated around and then moved downstream and then deposited. Now typically that can take a period of several minutes or even longer, and if your burnout time of embers is only a few minutes, then most of those embers will actually extinguish before they hit the ground. Whereas what we're talking about in a downslope wind regime, and also when we've got a hydraulic jump, is we've got the embers being transported over a shorter distance horizontally, or quite a rapid up motion and down motion. So in that scenario you're actually going to have more embers which don't extinguish before they hit the ground, which is consistent with the descriptions that we're getting of an ember storm rather than just a few embers. So if we go to the next slide, which is a blue slide with some wind vectors on, what we're looking at in this slide is high-resolution simulations that we've done. This is part of the coupled runs that we're doing on the Wednesday evening. And what you can see in there, hopefully you can see, sort of got Bustleton down the bottom, the black line is a coastal outline. It's quite a coarse grid coastal outline, and these are the near surface winds on the Wednesday evening. So what you can see here, and this is consistent with what we saw on the automatic weather stations, you've got quite light winds up on the scarp, and then those downslope winds are much stronger winds that are coming down the gullies and down the lee slope of the scarp. So there's an order of magnitude difference between what you're seeing in the broad picture, particularly on top of the scarp, and your downslope winds, which are highly localised but really strong flow. And importantly for Ember transport, they're really turbulent flow as well. So any turbulence is going to help loft the embers above the surface. So if you've got nice smooth laminar flow, you're actually going to get more embers dropping out of the flow, whereas if you've got turbulent flow, you're going to get more embers sort of being held up and mixed up by the turbulence in that flow. Now, hopefully what you can also see in that blue slide is there's a faint blue line or a region of lighter winds just to the west of the region of stronger winds, and that's a hydraulic jump. So that mechanism there is where you've got stronger winds near the surface, just at the edge of the scarp, which is your red, and then they bounce back up or wave back up in the hydraulic jump and then come back down. So you can actually see that it's resolved. The model's resolved the hydraulic jump mechanism, which when we start doing simulations is going to be really interesting to see how a fire behaves when you've got a fire in the coupled model, because we know that the way the model is resolved in the atmospherics is actually really strong. Are there any questions about that? Because it's a bit complicated and technical. No, everyone's got it. Good. So Warwick Grace, who is retired and does some consultancy now, he used to work for the Bureau. He's done quite a lot of work on the gully winds here locally in Adelaide, and he's run a high-resolution model. And what he's found is that in the gully winds you tend to get these hot spots. So you really get localised areas where you've got stronger winds. So down at the bottom of the lee slope, you can have really strong winds in a patch near a gully, and then you can move just a short distance away. And if you imagine if you were driving, it'd be over the course of sort of a minute or less. You can move from areas where you've got really strong winds to really light winds, which in terms of fire prediction makes it really interesting because you've got this highly variable wind regime sitting along the lee slope. So if we go to the next slide, this phenomenon has been studied before. So there was a really interesting example from the rattlesnake fire. Hopefully you've got a slide up at the moment that's got the rattlesnake fire. It was a study that was done by an American guy, Crum, back in 1954, and there were a number of fatalities when a fire basically was in a downslope wind regime. And there were 3 points that he made which I think are really interesting and really poignant from a fire behaviour point of view, is that the explosive behaviour is indicative of a change of air mass. So you've got a change of air mass and you've got a dramatic transition in fire behaviour because of this downslope wind regime. Secondly, he said there's high local variability in the wind strength in adjacent gulches or gullies along the base of the mountain range. So you've got this highly localised variability in the wind regime, which obviously can't be picked up by automatic weather stations, and we're only really seeing it, the detail of it, when we're going down to model resolutions of about 400 metres. So it's not necessarily going to be picked up. The detail of it might not necessarily be picked up by operational models when we're running them at a kilometre or more. And really importantly, from a management point of view, that the onset of downslope winds is really sudden and it's not associated with any visible signs that might signal the danger. And the other thing, of course, is that these downslope winds tend to pick up in the evening period and in the overnight period. So in the evening period, you're normally expecting to see a decrease in fire activity because the temperature's going down. Usually your winds go down. They don't in a downslope wind regime, and your relative humidity is coming up. So it's, in terms of the diurnal trend, the downslope winds are going to occur at the time that you're actually expecting fire behaviour to decrease. So on to the next slide, which is looking at the Pyro-CB event on the Thursday morning. So the fire, you can hopefully see from the isochrones in there, in the overnight period, the fire was actually reasonably quiet. It didn't run that fast. And then in the morning period, it took a big run to the southwest. So the run was from the northeast to the southwest in the morning period. And then interestingly, the fire behaviour quietened down again in the afternoon, and that was when your highest FFDI was. So if we go to the next slide, which has got an F160 showing the vertical trace for the Pyro-CB then on the Thursday morning. Compared to the previous day, the atmosphere is not as unstable, so you've lost a lot of the cape that you had on the previous day. It's a lot more marginal in terms of thunderstorm potential. But importantly, if you look at the low-level winds, so the wind barbs on the right-hand side, there's a lot of wind sitting just above the surface. So there's 40-odd knots of wind, 40 or more knots of wind sitting just above the surface during the Thursday morning. Now, importantly in through here, the automatic weather stations were showing an easterly wind, so your easterly wind being your surface wind, but the fire spread direction that we saw in the previous slide was going from the northeast to the southwest, which is much more consistent with what the winds are above the surface. So importantly in here, it wasn't the surface winds that were driving the fire spread during the morning, it was the winds above the surface. So the atmosphere generally was pretty marginal for thunderstorms. There wasn't a lot of activity around. But interestingly, this was in the morning, the event. So there were two separate pulses. The first one was about 11:30 in the morning. The second was about 1:30 in the afternoon. And normally when we're looking at sort of traditional thunderstorm activity, you'd be expecting it to kick off around about 3 o'clock in the afternoon for surface-based stuff, rather than in the morning period. So I think this probably caught them out a little bit as well, in that you had this pyroconvection developing in the morning, which certainly isn't a normal time for expecting to see deep surface-based convection. On this day, there was quite a lot of low-level wind shear, probably as well helped with the organised convection, and the anomalous spread direction, which didn't match the surface winds, was a real feature of this. Now, interestingly, if you flick back to the previous slide, which has got the isochrones on it, we actually had the fire burning along a really long line at this point in time. So continuous fire line was probably about 10 kilometres, and discontinuous fire line, because there would have been breaks in it, was probably around about 20 kilometres. So it was a really, really long fire line, which had developed in response to the changing wind direction round to that northeasterly. So what we think is that the long fire line was a really significant component of producing the amount of energy that was available to overcome the inhibition in the atmosphere. So if it had been running on a short fire line, you wouldn't have had as much energy released over the area, so chances are you wouldn't have got a Pyro-CB that morning. And we've seen other cases as well, other case studies where a long fire line is probably one of the key ingredients for producing either deep convection or Pyro-CB. And yeah, the last point on that slide, the F160 slide, is that those northeasterly winds were around about 28 to 82 kilometres an hour in the low levels, and that's consistent with both the direction of spread and also the speed of spread, whereas your surface winds weren't going to tell you either of those components of the story. So the next slide, which is a satellite image, an aqua satellite image, which was taken early in the afternoon. You can see the long, hopefully you can see the red fire pixels. It's a really long fire line, so nearly 20 kilometres long. And what happened on this day was there are actually two separate pulses of Pyro-CB. So the first one was about 11:30 in the morning, and you can see that's the cloud that's being advected across to the east. So once it got up above a certain height, and you can see from the trace on the previous slide, that once it got up around about 8 kilometres or more, it was actually in a different wind regime. So the wind regime that the Pyro-CB was experiencing was completely different to the wind regime that was happening down near the surface. So there was a first pulse which then got advected across to the east, and then there was a second pulse later on in the day. So a really complicated environment, but certainly there was nothing on the surface ingredients that were going to tell you anything about the fire behaviour. So if we go forward to the next slide, which is another radar image, you've got the reflectivity and the velocity. And on that velocity scan, it gives you an idea of the length of the fire line. So on the velocity scan, you've got red, which is away from the radar, and blue, which is into the radar. So what you can see in there was a really strong convergence along the fire line. Now this to me is a really interesting radar image, because it's one of the first examples that we've actually seen where you get an idea of how far away from the fire line the fire creates a change to the atmospheric winds. So up to around about 5 kilometres away from the fire line, you've actually got modification in the surface winds. It's not just happening just along where the fire front is. That fire is changing the wind environment to pretty considerable distance away from it. Now, hopefully in that slide you can also see the red pixels in the Doppler scan at the back of the fire. Now those red pixels, those are near surface, it's a near surface scan that we're looking at, but in the surface winds there wasn't a lot of wind strength. So those red pixels are actually the wind above the surface mixing down into the back of the head fire. So the fire there is actually entraining wind from above the surface down into the back of the plume, and that's consistent with work that we've seen on thunderstorms. Thunderstorms do the same thing, they entrain wind from above the surface, and it's also consistent with work that's been done, research work by Brian Potter in the States, where he's done conceptual models of what the airflow is around a fire plume. So the important thing there is that the fire plume is actually pulling wind from above the surface down into the back of it, and we've seen simulations that we did of fires on Kangaroo Island with a couple model actually showing that entrainment process. So another factor as well was that the fuels that morning hadn't been burnt for about 20 odd years. So it was a really long period of unburnt fuel, so there were heavy fuel loads as well, and that wind convergence really quite considerable. So on the next slide, which is the automatic weather station, again at Wagerup, this is the one near the bottom of the hill, we can see that through that morning period there wasn't a lot of wind around. So the temperature got reasonably warm, up around 40 during the day, but through the morning period the temperature was still rising, the relative humidity was 20–30%. Your wind direction at the automatic weather station had actually flicked around to the southwest because it was inside the convergence zone of the fire line, but importantly there wasn't a lot of surface wind. So the main point there is that during that morning fire run, the surface winds weren't giving you an indication of it, and it was the winds that were above the surface that were being mixed down. But also importantly, it was probably a combination of the meteorological factors and also the fact that we had a really long fire line that was burning in fuels that had pretty heavy fuel loads. So if you flick to the next slide, which has got a couple of pictures of the Pyro-CB event in the morning. In the late morning period, that FFDI was very high on the Dwelling Up automatic weather station. If you look at the slide on the left has got a lenticular cloud that's just sitting as a cap on top of the Pyro-CB, and that lenticular cloud is an indicator of really strong vertical motion in the atmosphere punching up. So that's where it hits the stratosphere, and that lenticular cloud developing as a response to the really, really strong updraft. Now, looking at the fire behaviour during the period, in the reconstruction, you can see on the images that they've got, there was really extensive defoliation during the morning. So during that morning period when the Pyro-CB was occurring and when the fire was doing its run, you had pretty extensive defoliation, but in contrast, in the afternoon when the FFDIs were higher, it had dropped back to crown scorch. So the intensity of the fire was less during the afternoon than what it was in the morning period, even though the FFDIs were higher in the afternoon and less in the morning. So the FFDI actually peaked at 54, again, same time as the previous day, at about 4:15 in the afternoon. And at that time, the fire activity was a lot milder than what it had been earlier in the day when the Pyro-CB was occurring. And a large part of that would have been the response to the winds that were above the surface. Any questions? No? No questions?
Hi Mika, can you hear me all right?
Yep, I can.
This is Nick McCarthy. I was just really interested in, and I'm not really sure if I grasped it, but in the access couple simulations, what's the scale of the pressure perturbation you'd be seeing in the field in that sort of 5 kilometre radius?
Don't know because we haven't got that far with the modelling.
No worries.
And in a year or so.
Yeah, okay, cool, will do. The other quick, more of a comment actually was really interesting is that some of the stuff we see in our radar scans as well is like a low-level horizontal flow. I mean, it's not necessarily being scientific here, but in the sort of high-resolution scans, you've got near the surface really turbulent flow as compared to any other periods during the plume, broadly associated with the periods of spotting from at least the Mount Bolton fire that we have. So just a comment there.
Yeah, that makes sense. And I think that turbulence, I don't know if you've seen the work that Will did with his plume stuff. Some of it. But the turbulence is obviously really, really important, and there's a lofting mechanism to help keep your firebrands from falling out. It's a really critical part of the process. So I think from a meteorological point of view, identifying those turbulent airflows as well is a really important part of understanding the spotting process.
Yeah, right. Do you know if the Perth radar had spectrum width available for that event at all? And have you seen anything in that?
No, I don't know.
Okay,
Sorry.
I'll follow up with that offline, but yeah.
Yeah. Any other questions?
Yeah, make Andrew again. The turbulence is giving longer hang time, you're saying? I thought it was going to lift the firebrands up and then dump them down more quickly, but you're saying they're going to hang longer with the turbulence?
Well, I think there's kind of two ways of looking at it. So if you've got a plume where you've got the plume developed and you've got particles or embers that are being lofted vertically, they're going to go up a long way, and then the turbulence will help keep them in the plume, which means that they can be transported for longer, and then they'll come back down again, and they may or may not be extinguished by the time they hit the ground. So what Will's stuff has shown is that if we're going to start developing spotting parameterizations, which is part of the plan, that will actually eventually come up with an operational model for predicting spotting, you can't do that for a fire plume without taking into account the turbulence, because it's got a really strong impact on what the landing distribution is going to be and how far the particles are going to get transported. Now, the other way to think about it is in terms of horizontal flow. So if you've got a low-level horizontal turbulent regime, then you're going to get particles firstly not falling out of the flow, because the turbulence is going to help keep them up in the flow, but also if it's horizontal, they're going to get transported a longer distance for a given burnout time. So if you've got particles, we did a bit of a back-of-the-envelope calculation just recently, but if you've got particles that have got a burnout time of, say, 5 minutes, and you've got a downslope wind regime where we know that at times the gusts can get up around 90 kilometres an hour, you can actually get a large number of embers transported a distance of a few kilometres, say up to 5 kilometres, within the burnout time of those embers.
Yep, that makes sense.
Does that make sense?
Yep, that's good. So just going back a bit with the plume development, and just so I've got the picture in my head, we're drawing the upper level winds down into the back of the fire. Yep.
And that's consistent with conceptual models of thunderstorms. It's also with work that Brian Potter's done, and also work that we did on the Rocky River fire on Kangaroo Island, when we did coupled simulations of that, and we used the wharf fire model to that. We actually did trajectories, and you can see in the trajectories that the particles or the airflow was sitting up above the inversion at about 1 or 2 kilometres above the surface, and then it got to the back of the head fire, and the trajectories the plume dynamics just pulled that trajectory straight down into the back of the head fire. So there's a lot of evidence and a reasonable understanding for how that works.
Mm-hmm. Very good.
Which really negates some of our use of surface winds for fire prediction.
Yeah, you can forecast when that's going to happen.
Yeah, and that's probably one of the interesting questions that we don't have a grasp on the answer at the moment, is how big a fire do you need in order to get those kinds of processes happening? Is it going to happen, are you going to get a lot of entrainment when you've got a small fire, or do you need a fire of a particular size before you're going to get entrainment for above the surface? Or is there a threshold in there that we don't really know about, or is it some kind of continuum? But it's certainly really strong evidence for looking above the surface and to look at what your winds are above the surface and whether or not they're going to mix down. Now, from a forecasting point of view, if we've got a really bad wind change day, we'll always mix those winds down in the grid, because we know that on a wind change day, particularly a hot day where you've got a deep boundary layer, you're going to get mixing of those winds that are above the surface down to the surface. But in other circumstances, the winds aren't necessarily going to mix down, but if you've got a fire there, the fire's going to help them get down to the surface, which is going to drive your fire spread.
Yeah, so I'm talking about the size of the fire. You know how the fire behaviour abated through the course of the second day. Did the fire line, the size of the fire line reduce? Like, did that, change direction? So you're talking about 10 or 20 kilometres of fire line. Did that kind of pull together so you didn't have as much fire as the day progressed?
I don't think it did, no. I'd have to go back and have another look at the reconstructions, or I can send them through if you want to have a look. But I don't know that there was a significant difference in it. There was certainly a lot of fuel out there, so where the fire was burning, it was actually in the mining envelope of the Alcoa mine, the bauxite. So part of the problem they had in terms of any kind of mitigation efforts was that there was a real mixture of old fuels and rehabilitated mining site, and a lot of limited access to it as well. So there was a lot of complexity to the fuels, and it's really hard to know the detail of how that impacted the fire behaviour as well.
Yeah. Okay, one more. Downslope winds we're talking about. And is there any lessons you can take out of the Californian fires, Verona winds, and what happens there with the downslope winds?
Yeah, so I don't know if you saw the hazard note that Jeff put out a little while ago on mountain waves.
Oh, yeah.
So essentially there's different... when you've got a mountain and you've got wind flow that's perpendicular to that mountain, all kinds of interesting things can happen with the wind regime. So we're seeing a lot, there's obviously so many case studies where if you've got a fire that's running through mountainous terrain and you've got winds above the surface, it can mix down. The downslope winds that we're looking at in this case, the gully winds, are a particular, subset of winds, in that you've actually got a wind maximum that's sitting quite close above the surface. So some of the other wind regimes, you've got your stronger winds that are sitting, 2 to 5 kilometres above the surface, whereas in a downslope wind regime, you've often got a wind maximum that's sitting just 1 or 2 kilometres above the surface. And the other feature that's important in the downslope winds in terms of the gully winds that we're talking about is that they tend to onset in the evening, whereas the ones that in California, for example, they weren't necessarily that diurnal mechanism. You've just got really strong flow, which is perpendicular to a mountain, and there you get that downslope wind response. But it's also consistent with the work that Jason's been doing, looking at the fires through Canberra. And there's example after example of sort of wind regimes perpendicular to mountain ranges, and the local flow, highly localised flow, being really unpredictable and mixing down from higher up. Does that answer your question, or not quite? Yeah. But yeah, the gully winds are really, or the scarp winds are really a particular manifestation. And interestingly, we've been looking at high-resolution simulations, and certainly in the UK, where they've got airports, they're really aware of that. So they've got a lot of airports which are on a flat area near a mountain range, and they're trying to develop better ways of prediction. And there are actually little algorithms that we can look at using where we can actually identify the areas which are conducive to producing these downslope winds. So that's one of the things that we've been talking about with the Extreme Weather Desk, is trying to develop some of those algorithms so that forecasters can actually look at them when they're looking at the forecast grids through Visual Weather, if you know the Visual Weather platform that the forecasters usually use. We're trying to look at, can we actually develop an algorithm where the forecasters have got ability to identify zones which are conducive to downslope winds. And then, of course, it depends if you've got a fire burning in the wrong place at the wrong time. But I think one of the main things with the downslope wind and the fire mechanism, and this goes back to the slide that I just showed on the rattlesnake fire, is that the transition is really, really quick. And we'll see that in the radar scan when we look at it in a minute, that the transition in fire behaviour and the onset of these downslope winds happens within half an hour or so, and you've got no real indicator, no real visual indicator that things are about to change. Any other questions? Nope. All right, so should we jump to the next slide, which is the Ember storm, the second Ember storm, which was over Yarloop on the Thursday evening. So with this one, it was a really rapid onset of the Ember shower after 7 o'clock in the evening, and this was a large part of what caught them out, was just a really dramatic fire transition. There were 2 fatalities and 166 homes were destroyed in total, and most of those were in the town of Yarloop. The radar, which I'll show you in a second, shows a really rapid increase in plume height from about 3,000 metres, about 3 kilometres to 8 kilometres, between just after 7 o'clock in the evening and 7:30 in the evening. So again, this is a period when you'd actually be expecting that your temperature's dropping reasonably quickly, so your fire behaviour would be expected to decrease. And the winds in this regime were also consistent with the downslope winds, although we had some problems with the model initialisation. It was producing some outflows that didn't occur, so we're going to keep on working on the modelling side of this, but the picture is completely consistent with your downslope wind regime. And the main message in here is the really dramatic transition in fire behaviour. So I'll go to the next slide, which is the automatic weather station again. At Alcoa. So we can see that in the evening period the temperature was dropping. Relative humidity stayed pretty low. There wasn't actually particularly good recovery on the relative humidity, and that would have been a factor for the fire behaviour as well on both overnight periods, is that there wouldn't have been good fuel moisture recovery in the overnight period. So that was certainly a contributing factor. Wind direction was an easterly, which is consistent with your downslope wind regime. And if you look at the wind speed, the bottom plot, the last section of it from 6 o'clock in the evening through until midnight, you had an increase in wind speed, which is consistent with the meteorology of the area, but you had this gradual increase in wind speed. So that doesn't reconcile with the dramatic increase in fire behaviour. So even though there was an increase in the wind speed and there was a bit of dry air coming in as well, that doesn't explain dramatic difference in fire behaviour over half an hour or so. So flicking through to the next slide, which is a description of the Ember storm over Yarloop. The fire activity escalated between 7 o'clock in the evening and 8:30 in the evening, and fire spread at this time was about 2 kilometres an hour. So really fast fire spread in the prevailing conditions, where when you looked at the nearby automatic weather stations and you looked at the wind away from that little downslope area, particularly up on the scarp, there wasn't a lot of wind around. Ewan Ferguson did the report of this fire for the WA government. A couple of quotes from that the fire just jumped in every direction, north, south, east and west, so there was no consistent direction of spread of the fire. And at one stage, every single boundary was like a head fire when, like it went through Yarloop, like the whole thing just exploded in a massive downdraft. So that description of a downdraft to me is really consistent with what we know about hydraulic jumps, where you're going to get a lot of outflow in all kinds of directions. So not a consistent wind regime from any one direction, but a really turbulent flow and a lot of outflows going on. So going through to the next slide, which is another radar scan. The key point here is that when you looked at the radar scans, the velocity scan in particular, just after 7 o'clock in the evening, you had a really light wind regime. And when you look at the vertical profile of it, which is the bottom right plot, all of the plume returns were sitting around about 3 kilometres. So there wasn't actually a particularly deep plume. Going through to the next slide, that shows the reflectivity and velocity scan at 7:30, so only 20 minutes later. And what you've got in there is the plume height had actually increased to over 8 kilometres. You can see that on the bottom left scan in the velocity, the vertical cross-section of the velocity. So the plume had increased in height from about 3 kilometres to over 8 kilometres in the space of 20 minutes or so. And importantly, on the top right scan, you can see there's an area where there's a strong red and a blue quite close to each other. So that's an indicator of really strong convergence. And that is pretty much over the town of Yarloop. So the radar's actually showing that you've got this really strong convergent mechanism, which is of course a lofting mechanism for embers. And at this time, what also happened was that the fire ran into an area of really heavy fuels just to the east of town that hadn't been burnt for 20 years or more. So possibly the fire ran into the heavy fuels, there was an increase in plume height, and it coincided with the development of downslope winds and maybe even a hydraulic jump, which is quite likely. And then that produced a lofting mechanism to lift a whole heap of the embers from that heavy fuel area, lift them up quite rapidly, 1 kilometre or 2, and then deposit them back down quickly over the town, with most of those embers still being within their burnout time, because it's going to happen as a really quick mechanism. So it's going to happen over the period of a couple of minutes, rather than all these embers sort of being turbulent and moving around and extinguishing before they hit the ground. And that, to me, is consistent with the description from the Ferguson report of a massive downdraft and an ember storm, rather than just a few scattered embers. Any questions? No. Okay, so if we go to the next slide, so we've got two schematics of how the downslope wind regime might work, and these were done by one of the guys in the Bureau's graphics department. So we've got a mountain range. You can see the colour difference in the blue indicates a temperature inversion near the top of the ridge. You've got an airflow which is coming up the back of the ridge. It gets squeezed near the top, and as it comes to the slower flow downstream, you've got the airstream coming up the back of the hill, accelerates downwards, and you can get this up and down hydraulic jump mechanism. And if you've got a fire that's burning in the wrong spot, and interestingly, of course, a lot of these lee slope areas, particularly where we're talking about the mountain ranges in Western Australia and South Australia, you've actually got quite high rainfall on those lee slopes. So they're good environments, high rainfall, lots of fuels, lots of heavy eucalyptus fuels, which can produce your embers. And they're also areas where people like to live. So you've got this potential for seeing a lot of transport of embers up and down over a period of a couple of minutes, which means that it's inside the burnout time of the embers, so you're going to get a lot of deposition, quite heavy deposition locally, which is consistent with the description of the ember storms. And then the second mechanism, which if you flick to the next slide, which is another schematic which is a little bit different, you've got the same sort of motion in terms of your downslope wind regime, but without the hydraulic jump. So you can move embers a reasonably short distance really quickly, and because it's turbulent flow, they're going to keep on being lofted up in the flow, and you can get transport to, over the period of probably at least a few kilometres within the burnout time of the embers. So along those lee slopes, obviously, it's it's an area that's conducive to seeing ember showers and ember storms in the evening period, but you've also got fuels that are conducive to producing the right kind of firebrands, and also a lot of properties. So moving on to the next slide, we've got the lessons from Waroona, the first slide. Downslope winds, Perth winds, Adelaide gully winds. There's been I had conversations with people in Victoria who have aware of fires where they think a similar sort of thing happens, where you've got that turbulent motion. I'm sure that if we looked at the environments, I haven't done it yet, but if we looked at the environments in both New South Wales and Queensland, we'd find localities, we'd find areas where they do get these downslope wind regimes, which are be favourable for the kind of process happening. Importantly, the timing is against the normal diurnal cycle. So these kinds of events are likely to happen in the evening and in the overnight period, where you'd expect your fire behaviour is actually going to decrease, and the turbulence is going to be conducive to ember showers, and the turbulence is going to help keeping those embers lofted in the air. The second point being the pyro-convection. Your downdrafts can be separated from your updrafts and get erratic outflows as well. So erratic winds coming down to the surface, which mean that you can the fire can then spread in unexpected directions and at speeds that are much higher than what you'd expect from the environmental winds. New lightning ignitions downwind, and the lightning ignitions downwind can be in a different direction to where your spot fires might be. So you might have a different wind regime in the lower levels of the plume where your embers are going to be compared to at the high levels, which is where your lightning ignitions are going to be directed. So you might have ember transport, to the west in the low levels, whereas you can actually have lightning ignitions to the east in the higher levels. And obviously at the Waroona fire we did see new lightning ignitions downwind, and that didn't reconcile with where they thought the head fire was going to be. Pyro-convection does appear more likely with long fire lines. There's a few cases now where you've got long fire lines, higher energy release, and that's producing pyro-convection, and also along change boundaries, so frontal change boundaries, whether it's a sea breeze front or whether it's a synoptic front, it can trigger pyro-CB where it wasn't otherwise expected. Moving on to slide 2, the second slide, the timing of the maximum FDI. Importantly at Waroona on both days it was about 4:15 in the afternoon, and that didn't match the time of any of the extreme fire behaviour events, and we've seen that in other cases as well. The main thing is that the key meteorological ingredients were above the surface, so your MacArthur framework looking at the surface conditions was never going to tell you or never going to anticipate the likelihood of extreme fire behaviour, but all of the ingredients were above the surface in these cases. And importantly, when we look at the extreme fire behaviour, it was a combination of factors. It was the fuels and the winds and the topography and the instability all working together. So it wasn't just a single factor, it was the interactions between them that produced the extreme fire behaviour. So what I might ask you to do now, if it's all right, Greg, if you can run the video, which was the video of the Waroona fire, which was taken on the first evening by a guy called Darren McCarr at Farmhouse Films in Western Australia, and he did that as time-lapse photography.
Yep, we're just loading it in now, so just bear with us. Okay.
Thank you.
We'll let you know when it's about to start. Chris is just doing the magic at the back end here for us.
Thanks, Chris. So you can see, when we get the video up, you can see the multicellular nature of it. This actually punched up to 15 kilometres above the surface, so it would have actually put emissions into the stratosphere, which are probably still circulating around the globe now, or they will be for years to come. So all the emissions go up into the stratosphere and contribute to greenhouse gases as well as other complicating factors. You can also see in the plume that it's really turbulent, and you can also see when the video's running that there's actually wind at different directions at different levels. So you can see that steering winds are at different levels, and you can also see the rotation in the plume as well. There's really, really strong rotation, and that would have partly been contributed by the organisation in the wind shear, so that vertical wind shear that we were talking about earlier.
Yeah, so we just about got through it once while you're talking. We're at the credits. Yep. What we can do is we can run it again for people. Yep. It's probably better if they do it at full screen. So we'll just start it off again now, Chris.
And if anybody wants a copy of that or wants to try and see a copy, it's still on the web, I believe, at Facebook. And if you go to Facebook and search Waroona Farmhouse Films, it'll pop up.
Yep, so it's running again now.
Yeah. So if you want to have another look at it, go to Facebook and search Waroona Farmhouse Films, and you should get it.
That's it. Yep, okay, it's gone through again for you. Back to you, Mecca.
All right, any other questions? So the paper, we've written a journal paper on this, and it is now online at JSHES, so the Journal of Journal of Earth System Science, Southern Hemisphere, JSHES, which is on the Bureau website. So if anybody wants the longer version and the full paper, it's available as an online early release now. and it will also be available as a sort of nicely typeset copy, hopefully in a few weeks.
Are there any questions of Mika?
Nothing from Queensland, just thank you.
Yeah, equally. Thank you for that, Mika. That's the results of some really hard work on your part, but some really interesting outcomes from our point of view, and probably from the BRI forecaster's point of view of stuff we haven't traditionally been looking for, or if we have seen it, we haven't known what we've seen.
Yeah,
so
and I think
really
that's one of the things that struck me talking to different people and talking to operational people around the country, is that when you start describing these things, people will say, oh, I reckon that was what happened at that fire at such and such, and we didn't understand what was going on. So the descriptions really do match in well with people's observations and experiences at other fires.
No, that's great. Thank you very much.
All right.